So now we'll discuss diffraction. So generally we know that light seems to travel in straight line. Okay, but if you observe very carefully, then you will see that light does suffer some deviation from its straight path when it passes very close to the edges of any opaque obstacle or any aperture, like very narrow slits. Okay, and it is found that some of the light bends into the region of the geometrical shadow of the aperture or the obstacle. So here you see, generally, suppose over here we have a parallel beam of light passing in this direction. Over here we have an obstacle, an opaque obstacle. Okay, so that light cannot pass through it. And over here we have one screen. So we should get a shadow of this obstacle on this screen. And what should be the shape of the shadow? The shape of the shadow should be the same as the geometrical shape of the obstacle, which is in this case a rectangle. Okay, so generally we should observe that we get a very precise rectangular shadow. Okay, rectangular shadow on the screen, and all these regions will be illuminated other than the shadow. But what is observed that around these edges, okay, over here in the geometrical shadow, you will find some illumination, which is not possible if we consider the rectilinear propagation of light, that is, the light travels in a straight line. Okay, so it appears that when the light ray is passing around the edges of the obstacle, it bends and enters the and reaches the geometrical shadow of the obstacle. Okay, and in case also, suppose over here we have an rectangular aperture through which light can passes, and these areas are blocked. Okay, so when the light rays are passing through this aperture, so we should get a rectangular, so this is a rectangular aperture, we should get a rectangular portion which is illuminated, and the other portion on the screen is completely dark. Okay, so but what is observed that this region, okay, just around the geometrical shadow of this cardboard, you can say, which is having the aperture, is illuminated. So it appears that as if while light passing through the around the edge of the aperture has bent and reached, there is some bending of light ray and has reached the geometrical shadow. Okay, same goes for this area, this area, this area. And here also, okay, so around over here there is some illumination. So as if light ray has bent, okay, from its general propagation in straight line. Okay, so and this phenomenon is more prominent or more observable if the wavelength of the light ray we are using is comparable with the dimension of the wavelength and comparable with the dimension of the obstacle or aperture. Okay, so this phenomenon is known as diffraction of light. Okay, so we can define diffraction in the following way, that bending of light around the edges of opaque obstacles or aperture and spreading of light into the geometrical shadow of that obstacle or aperture is called diffraction. Okay, and this phenomenon of diffraction is more prominent when the dimension of the obstacle or aperture is comparable with the dimension of the wavelength of the light. Okay, so but even in such cases the phenomenon is observed on very careful investigation. Okay, so how this, so here also we can observe, if we are using some suppose some light rays and some obstacle or aperture, and we can observe the diffraction pattern just like the interference pattern on this screen. So how the interference is different from the diffraction. So here you see, in case of interference, generally we use this kind of setup where we have one source Okay, and the light rays, here we are showing the wavefront. Suppose generally if we are using a point source, so the wavefronts will be spherical waveform. Okay, reach slits, so there are two slits, one over here, another over here. Okay, so we generally use two slits, or we have to produce two coherent sources, or like Young double slit experiment, we are using two narrow slits, identical narrow slits. Okay, so when this wavefront reaches this two slits, which two are equidistant from the source, the only on the opening of the slits, the wavefronts can pass through them. Okay, another portion of the wavefront will be blocked. So in this case it have this being very narrow, these two slits will be acting like point sources, and they will generate secondary wavelengths. Okay, and these two secondary waves, as you can see that they will superpose, and we can observe an interference pattern on the screen. Okay, interference pattern can be observed on the screen. Okay, so interference, we can say that interference is the result of interaction of light coming from two different coherent sources, like this, two different coherent sources. Okay, which is originating from the same source. Okay, whereas if you look at the diffraction, what happens? Suppose over here we have some source. Okay, and it is generating, suppose, spherical wavefront, and then over here we have one suppose aperture. So this is the aperture, so there is some opening, and if the dimension of the aperture is comparable with the wavelength of the light, then we can observe then the light suffers diffraction, that is the light rays will bend around the edges of the aperture. So when you see, when this wavefront reaches this aperture, each according to Huygens principle, each point on this wavefront will act like a secondary source. Okay, and all this secondary source on this opened portion of the wavefront will generate these secondary wavelets. Okay, so these secondary wavelets will travel in every direction. Okay, so as you can see that generally light should reach only these 2 points. Okay, in this about the which is just in front of the opening, but as you can see that these secondary wavelets can travel in every direction. They will spread in every direction in the wave, in the forward direction. That's why light will also reach in the geometrical shadow of the aperture. Okay, so in this way you can see that light rays reaching above this this region, suppose PQ. Okay, above P and below Q, this is the geometrical shadow, but these light rays are reaching this point. Okay, so that's why this is the bending of light, which is the diffraction phenomena. So we can say that the diffraction pattern, so, and we can observe the diffraction pattern on this screen. So you can say the diffraction pattern is the result of the interaction of light coming from different points on the same wavefront. So here what happened in case of interference, we created two coherent sources by dividing the wavefront into okay, and here what happens that here the interaction of light happens, interaction between secondary wavelets happen between the different secondary point source on the same part of the wavefront. There is no division of the wavefront. Okay, and later you will see that in case of interference fringes, you found that every fringe has the same width, but in the case of diffraction pattern we will see that the fringes are of different width. Okay, and you found that in case of interference the fringes had the same intensity, but in case of diffraction pattern you will find that the fringes have different intensity.